Nope. Okay. Is that on? I have no idea. Okay. Test. Good morning. Oh man, it's 2 minutes. That's 2 minutes. Ooh. Ooh. Yeah, Blue Moon there. What's going on? Caleb, I'm pretty sure not supposed to be drinking Blue Moon. No. In class, yeah. Dry campus, dry campus. Luck. There's a fight in there. All right, guys, it's 11. Which means we're going to get started. All right. Lord, thank you so much for allowing us to have this opportunity to come together today. I pray that you would just give us what we need for the rest of the week. Help us to stay focused on the things that are important and to get things done that we need to get done. In your name we pray. Amen. All right. So I know you're all very sad. It's the season finale, so to speak. Except you should probably come on Thursday to take that quiz, unless you're feeling particularly good. Then anyway, before we get into recap, this is what we're gonna do. We're gonna recap. We're gonna talk about moments of inertia, and then we're gonna do some quest prep. So that's really what I want to hit today. But before we get into that, you guys have probably received hundreds, if not thousands, of emails from the university asking you to fill out your end of course surveys. Yes, the EOCs, right? If you want them to go away, the easiest way to get them to go away is to fill out the EOCs. I would ask that you please fill out the EOCs. When you're filling out your EOCs, I Well, first of all, there are very few times in your life when you leave here that people are actually going to ask you for your opinion and actually use it to drive change. And that's what the EOCs are all about. If there's stuff that we were doing in this class that didn't work, I need to know about it. If there's stuff that was particularly useful, we can do more of it, right? But I need that information from you guys. So my one thing is you have to be constructive with any criticism that you give. Saying, I hate statics, it sucks, is not, it's not constructive. You have to tell me why you think it sucks. Okay, you can say, so rephrase it as, I hate statics and it sucks because, and then list the reasons, all right? Or if you like something. But please fill those out. Please leave some feedback. It does drive change. There was a time not so long ago when this class was statics and dynamics combined. And EOCs helped to drive that into us splitting it, right? And so same deal with transport phenomenon. Heat transfer and fluid mechanics used to be a combined class, which I don't know whose idea that was, but it wasn't a good one. Now it's split, but those are all things that happen through EOCs, right? So please fill them out. Or if you don't want to fill them out, be prepared to keep getting hit over the head with emails asking you to fill them out. All right? Yeah. Why is there no lab for statics? It's really difficult to come up with a lab to prove that things are in static equilibrium. For the long and short of it, but it's because it mimics a lot of the things that you do in physics 1. So a lot of the labs have crossover and it would not be a value add in that sense. We do have some, like, there's one lab that we used to run in ESG-260 when it was statics and dynamics together. We have these plastic trusses that you can build, and they have force sensors that go in between, and so you can do method of joints, and then you can check on an actual truss. But that's one lab, and one lab doesn't fill 15 weeks of lab space, turns out. But anyway, once again, any improvements that you think can be made, anything that you particularly liked, anything at all that you have comments about this class are welcome. So please fill out your EOCs. Recap. Last time we talked about center of mass, center of gravity, and centroid, right? Center of mass, I misspoke last class. I was going quickly. Center of mass and center of gravity will always be in the same spot, guys. They will always be in the same spot. But why? Why is that? Because the weight is the effect of mass in a gravitational field. All right. So just keep that in mind. CM and CG always end up in the same place. The centroid, the center of the geometry, might not align. When we have things that are all uniform, right, then yes, center of mass and center of geometry, centroid, will align. But if they are not uniform, then they won't. How do we calculate it? Well, we use these equations, right? Whenever we are asked to find a centroid or a center of gravity or center of mass, we are really we're hunting for coordinates, right? We're hunting for X bar, Y bar, and Z bar, right? And that is pretty consistent nomenclature no matter where you go in the engineering world. There are certain times where Greek letters get reused and they are different for different things, like omega will sometimes be frequency, but it will also sometimes be angular velocity, but those two things are actually kind of the same thing anyway, so that's a bad example. There's other ones, right, that are escaping me right now. Beta is one of them, right? Beta is the Stefan Boltzmann constant in heat transfer, but it is used differently in other areas, right? Anyway, how do we find that? Well, we can do this integration, right? We can say that X bar is equal to the integral of X tilde. Remember, X tilde is the distance to each of our individual infinitesimally small pieces of our system. So when we're doing this integral, right, we are breaking our system into an infinite number of particles, and we're saying that each one of them has some weight, and we are summing the effect of those forces, right? We've created a distributed loading, and we're summing all of that together. We're trying to find where is that all coming together, right? If we extend this, right, we can just substitute in M for the weight, or we can put in V or A or L, right? We can use whatever quantity we want in here, right? Use whatever quantity we want in there. Great. So those are nice, and I know everybody's got those written down. Big thing to take away is what's the difference between X bar and X tilde, right? And we'll talk a little bit. Well, I mean, the difference is that X. All right. So when we're doing the integration, right, and we'll talk about that here. Right. So I want to integrate the centroid of an area, right? Great. What do I have to do? First, I have to choose an appropriate differential element that I'm calling dA, right? At some generic point xy. So I go somewhere into my function, right? I pick thing, I draw a rectangle, right? We'll typically know what that function is. It doesn't make sense for me to ask you the centroid of an area if I don't at least tell you what the function is. In fact, it's impossible for you to be able to do that, because if you don't have a function, how are you going to integrate it? But there we are, right? So typically, if y is easily expressed in terms of x, I think this is a dumb rule. Right. And the reason I think it's a dumb rule is because if I tell you that y is equal to x squared, I can just as easily tell you that x is equal to the square root of y. And it's the same thing. It's the exact same thing. If I have an equation, if I have a function, I can very easily go from one to the other without any issue, right? So really, right, it says if y is equal to something, then use vertical elements, or otherwise use horizontal, right? And at the end of the day, it doesn't really matter if you choose rectangular or vertical or horizontal, right? That doesn't matter. The idea here is that we're going to create a infinite amount of rectangles that have some differential area, and we're using rectangles because those are the easiest functions for us to create an area for, right? That simplifies down greatly. And then we express our differential area in terms of dx or dy, and then we just take the integral over our bounds, right? And it's always a definite integral. It will never be an indefinite integral, because shapes in the real world turns out that they are bound by some physical limit, right? Great. Then we determine our x tilde, y tilde, and that's the centroid of all of our rectangular element that we drew at our general point. And we express all the variables and integral limits in the formula using either x or y, depending on which element we use. So if we use a vertical one, right, the reason I like to use the vertical one, because then typically none of that weird gapping that happens where I have to say 1 minus x times some, I don't have to get creative with my distances. It's just delta x and then y to where it touches the function, right? Okay. It's the same thing for CG and CM. All of these are the same, right? And that comes from this, right? And you can very easily see how we went from weight to mass, right? We divide the whole thing by gravity. That's how we get from weight to mass. If I wanted to get to volume, right, density is equal to mass times volume. So volume is equal to mass divided by the density. So if I divide all of these by density, I'm left with the volume, right? If I wanted to go to the area, right, I could go, that's a downgrade from the volume, right? I have to divide by a thickness. And if everything is the same thickness, it just happens. I said this yesterday, I will say it again. It's very rare that I would use this method if somebody asked me for the centroid of a length, right? Very rare. And in fact, by that I mean zero. I would just take the midpoint of the length, right? That's what I would do, because that's the centroid of the length. Now, what's the length's a curve, Dr. D? Well, then that's not really a length anymore. That's an area, because you're using you would use like a semicircle or whatnot to figure out where that is. Sometimes it's not. Remember, sometimes CG and CM and centroid are not on the object themselves, right? And so just be aware. Okay, great. So those are the steps. What happens if we have a composite body? Those are fun, right? If we have a composite body, we can kind of simplify our process, right? So instead of having to take a bunch of integrals, we are going to use just the sum of some things, right? And so we have these, remember, W, M, weight, mass, area, volume, all interchangeable in these. And this is really nice because instead of us having to take the integral of every section, we just have to make sure that we are bookkeeping, right? We are tracking all of our weights, we're tracking all of our masses, we're tracking all of our areas or our volumes, right? Then once we have the total weight, we have to sum up all of our x tilde times w's. There's no tilde there. There should be a tilde there. These are x tildes, right? So we find some point and we create, remember, x tilde for each of our particles or each of our portions. Okay. These can get tricky, right? I know that there's a homework problem that uses different materials for a piece, right? And asks you to find the center of mass or the center of gravity for that thing. Don't get tripped up by unit conversions. My suggestion for every engineering class that you will take from this point on is whenever you are given units, convert it immediately to base units. So kilogram, meter, and second, or foot, pound, second, right? And do all of your math in the base units and then convert as your final step. That would be my suggestion. Otherwise, you're going to get weird things like megagram per millimeter cubed, right? And that's super great and all, but it's not as meaningful. And especially when you're talking about center of gravity or center of mass, if you can get that to come out in kilograms, it's very easy for you to then tell me what the weight of that object is, right? Okay, great. So things that we keep track of, the weight of each piece in this case, and this piece, which we call the first moment of our area. Typically, if we're using an area, it's the first moment. So we need to calculate these, and that's where we use the table, right? I think a table is really helpful to keep track of it. You guys can do it however you like, though, right? I would highly recommend using a table, though, just to keep track of everything, and it's all in one spot. All right, x, y, z, tilde. So integrals. Integrals allow us to determine the area under a curve. Why is that important? Because when we were talking about centroids, we were talking about the geometry of some curve, and we want to find the center of the area of that curve, right? Notice that we don't do it for volumes. We can do it for volumes. Drawing it for a volume is a real pain in the butt, because then you have to use like a rectangular prism to do the pieces. Whatever, it's the same process. Don't overthink it. So why are we doing these integrals, right? Because essentially, what an integral actually is, right? An integral is actually us using those Riemann sums and taking the limit as x goes, the size of our rectangle goes to 0, right? So if we think about what the definition of an integral is, in the same way that the definition of a derivative is made, right? The definition of a derivative is that we have some change in one variable and some change in another, and we drive it as the change in the variable that we are looking at goes towards 0, right? Same deal for an integral, right? Except that the variable we're changing is the width of that rectangle, because we want as many of those rectangles in there as possible, because that gives us the best resolution for that volume, right? So integral is just summing all of the things in between our 2 points, right? So for this case, it makes it really nice. Now, there are certain textbooks that will tell you that you can do double integrals in x and y direction at once to get the stuff that you need. Don't worry. Use the stuff that we've talked about here, right, in the class, right? I didn't talk about double integrals. We're also not going to do any weird partial differential equation stuff because the level of math that you're supposed to have to come into this class is like Calc 2, right? So that's where we're at. So we're not going past that. Centroids. Centroid is a very special name for the center of our geometry, right? So I think we talked about this, right? But if you have an axis of symmetry, your centroid has to lie on that axis of symmetry. If you have multiple axes of symmetry, it will be where those three axes meet, right? So in 3D, if I have a cube, where's the centroid of a cube? Well, I would hope that it is dead center in that cube, right? Just based on the geometry, just based on the volume, okay? Why? Because I could fold it three different directions in half, and where those three intersect has to be that, right? We saw it a little bit with the semicircle yesterday, right? If you fold a semicircle in half along the y-axis, our centroid is along that center of that circle where we folded it. It's going to be a little bit up, right? But it's on that line. Riemann's, I'm not going to ask you guys to do Riemann's to figure out areas under curves. That was more of an aside to kind of contextualize what integrals are actually doing. X, Y, Z tildes, those are, so when we have composite bodies or we have multiple particles, right? What we are going to do is we need to find the coordinate to the center of each of those pieces, right? And that's what the tilde variable signifies. It is the center of our pieces, whereas x bar is the center of the whole thing in the x direction, all right? So remember, we're looking, in order for us to know where the center of an entire object is, we need to know where the center of all of the pieces are. And the tilde is if we break it down into pieces, where are those centers? A lot of times with composite bodies, we rely on the tables in the back of the book to tell us where that center is going to be, right? We are very comfortable at this point with triangles and rectangles, right? Because we use triangles and rectangles a lot when we are doing distributed loadings. And so everybody should know where the X and Y centroids of those objects should be, right? But you will get a table of all the other shapes, and you're probably not going to need most of them, but you'll have them if you want them. So there you go. Okay. Beams. Beams are members that carry loads, I guess. Yeah. We'll talk a little bit more about beams later. We'll go over that too, but shear, we didn't really talk about beams or shear yesterday. So I think that kind of, all right. Is there anything else? Anything else anybody wants me to cover before we move off of this? No? No? All right. Cool. So homework due tomorrow. And like I said, there's a quiz on Thursday. I would recommend doing both of these things. You check out the Yelp review if you want. Anyway, okay, and here is the final Dr. Deism of the semester. I know, so sad, tier, single tier, right? You can't make decision based on what ifs. Okay, I know a lot of people. So I've had students come into my office and say, "What should I do, Dr. D? I have this job offer, but there might be a better job offer." I say, "Well, is there another job offer? Are you in the pipeline to be hearing back from somebody?" And if the answer is no, then you should take that job offer if you think it's something you want to do, because you can't make decisions based on what ifs, right? You have to make decisions based on your facts and your data and what is, not what could be. Okay. Now, that's not saying you shouldn't plan for things that you want to happen, right? You should definitely do that. But when it comes down to it and you need to make a decision, right, you have to be in the here and now. You can't be someplace else. Okay. Moment of inertia. So, why do we care? Well, let me ask you this. Why do ice skaters pull their arms in during a turn? Because they're better. Because they're better at skating than Colin. Probably. Probably. Um, why do you guys think? What happens? All right, so you guys ever been on the most dangerous piece of playground equipment, the spinning metal wheel of death? Yeah, yeah. What happens if you are standing towards the center of that? It's really not that big of a deal, right? But as you get closer to the edge, you start to really, really feel it. The amount, the amount of force generated outward is more than when you're inward. And so if you are now pulling all of that in, you're actually in a better position to actually spin faster when you change your moment of inertia being extended to being in. Okay? You're pulling all that mass towards the center, which allows you to spin faster. Okay? Which is easier to turn, a big wheel or a small wheel that has the same mass? The smaller one, because all of its mass is concentrated towards the center, right? It's all towards the center. Okay, and this is the idea of moment of inertia. So today we're going to be able to define MOIs, or moments of inertia, and determine a moment of inertia for an area by integration. So I'll show you how to do it by integration, right? And I'll also show you how to do it for composite bodies. We'll talk about radius of gyration also, which is a cool idea. Um, so many structural members like beams and columns have different cross-sectional shapes like I, H, and C. So why? Why not just use a rectangular, solid, or a square or circular cross section, right? Why would we care? Right? Well, we would care specifically because of first of all how we carry the load, and second of all, are we expecting bending, right? What are the conditions that we're expecting? And it turns that this shape changes the moment of inertia, right, which rolls into bending and how much torque we can actually put on something. So what primary properties of these members influence the design decisions, right? Well, clearly there's some reason why an I-beam is uh, is beneficial, right? We use them like all the time. And it's because they're strong in bending, right? They're strong in bending. Okay. What about why do we have many structural members that are made of tubes rather than solid squares, right? Well, part of it is space, is weight savings, right? You know, I like it to be lighter, so I use square tubing instead of a solid piece of aluminum bar, right? But it also has to do with the moment of inertia as well, right? Um, so we're going to talk about specifically how do we calculate this moment of inertia. So does the sum of the force always equal 0 outside of this class? No, it does not, right? So what about the sum of the moments outside of this class? Does that equal 0? Turns out that the sum of the moments is equal to I times alpha, which is the moment of inertia times the angular acceleration. Okay. Now, why is that important? Well, in the same way that mass times acceleration is important. So if I have something that I am applying a moment to, right, the mass moment of inertia is sort of a measure of the minimum amount of it's kind of like the mass. It's like the rotational version of mass, right? And so we think of mass as like the minimum that we would need to overcome to kind of move something, right? So if I have just something sitting on a table and I want to lift it up, I need to be, if I want to hold this out like this, I need to be applying the weight of this, right? I need to be holding it with its own weight. Similarly, if I want to rotate something and keep it in position from rotating, right, I need to have at least match moment of inertia. So moment of inertia is really a measure of how much energy it's going to take to rotate something. Okay. Um, so say we have some given vertical loading P on a beam. This is not a beam. What? Okay, great. So it's on this beam. Obviously, it's right here. You can see it. Um, uh, which shape will develop less internal stress? All right, let's skip that part. All right. So for the differential, so we're using the bottom. We're using the bottom part only. Don't look at that. Oh, you already saw it. Oh my gosh, so embarrassed. I didn't want to do that one. Yeah. Wanted to do this one. This is the new TikTok channel that I'm starting. Is Dr. D redacts his own PowerPoint slides. Um, for the differential area dA shown in this figure, okay, and that what a differential area this is, right? It's super great, awesome looking. Everybody loves this. Um, we can show that the moment of inertia in the y direction is equal to x squared dA. The moment of inertia in the x direction is y squared dA. And the polar moment of inertia is, or the change in the polar moment of inertia is r squared dA. And the polar moment of inertia is measured from about point O or the z-axis typically. Okay, okay, great. Now I'll have to unredact this to move to the next one. I would probably write those down, right? Maybe. Or you could just write down what happens, right? So the moments of inertia for an entire area are attained by integration. In the same way, all right, so why? Why are we using integrals again? Because there are some properties that are a function, right? This is clearly somehow a function of the area that we are looking at, right? And if I want the area of something, I need to take the integral of that function, right? I want the area. Moment of inertia is clearly linked to the area, right? It's linked to the size of an object, okay? So moments of inertia for an entire area are obtained by integration. We've done this, right? You can do the vertical, you can do a horizontal, right? We also call this the second moment of the area. And I want you to look at how it's defined, right? If I want the moment of inertia in the x direction, I have to calculate the moment of the area using the y function, right? This is the y distance. If I'm doing it in the y direction, I'm using the x distance, right? This should also indicate to us which variable we should want as the differential in our area, right? So if I'm doing the y direction one, I want this to be area to be a function of dx, not of dy, right? And the polar. The polar is Ix plus Iy at the end of the day. So if you can figure out Ix and you can figure out Iy, the moment of inertia in the X and the Y, then you can figure out the polar. Why do we care about the polar? It's telling us about the rotational properties of our moment of inertia. Okay? So what units does moment of inertia have? If you were looking at this, what moments would you say that it has? Remembering. So let's just do a simple what if integral over my area. What units would that have? And we'll say, let's make this even easier. We'll say we're doing this for the example of y is equal to x, right? Because if we're going to take the integral with respect to x, we should probably have everything in terms of x in there. So what units would you say that that has after you take the integral? You had to guess. I mean, all right. That's before you take the integral. So yeah, it's to the fourth, which is weird, okay? Because you have this, right? you have this unit of length to the fourth power. So you end up with meters to the fourth, or inches to the fourth, or feet to the fourth, whatever your unit of length is to the fourth power. And you're like, one time I had somebody ask me what that even looks like, right? And it's basically it's a hypergeometry is what it comes down to, because it's one level higher than a volume. So basically, unless you are an ascended being, you can't perceive this. There's all stuff on YouTube about all the crazy alien stuff and those people. Yeah, not per. Right. So yeah, it's a volume times a length, right? But how do you determine, like visually, I can't show you a fourth dimensional shape, right? Because that's outside of three dimensions. So the way that I kind of think about it is like this. If I had um, if I had like a cube, right? And then I was able to see how this cube changed in time, right? That would kind of start to show you, but it exists in the same spot at all times, and you can see all of it at once. That's not really helpful, right? So what does it really look like? Don't worry about it. It's about the math, because what's going to happen is let's do one. Let's do one, and we'll see. Well, because what do we want out of this, right? We probably want to figure out X bar and Y bar at some point, right? And so that might be helpful, right? So let's just see what happens, right? But it's a fourth order length, right? So for simplicity, the area element used has a differential size dx or dy, right? In only one direction. Same as we did before. So we're making this rectangle, right? Make the rectangle. We say this is a generic rectangle. It's going to have some size dx, right? And some height dy or some height y, because the top of it will always touch my curve at some point, right? And then I can take those rectangles and do something with them. So step-by-step procedure is pretty similar to how we find a centroid, right? First, we have to define the differential area, right? So we have to select, are we doing vertical or horizontal, right? And that comes with a couple of considerations in this case. And that's because if we go back to this equation, you can see that one of them is determined in the y direction and one of them is determined in the x direction, right? So which one makes the most sense? Okay, well, first, the element parallel to the axis about which the moment of inertia is to be determined usually results in an easier solution. So for example, we would typically choose horizontal strip for Ix and a vertical strip for Iy. Okay, sure, sure. I will probably, unless held at gunpoint, I always choose vertical strips. All right, and it's personal preference, but you can do it however you like, right? But that's a thing. So if u is easily expressed in terms of x, which I don't know why we're using u now, but there you go. So if our function is easily expressed in terms of x, like x squared, y is equal to x squared plus 1, should probably be y, then choosing a vertical strip with a different differential element dxy may be advantageous, right? I think that we've been saying that. I, again, would argue that it is just as easy for me to say that that is y is equal to x squared plus 1 as it is for me to say that x is equal to the square root of y minus 1, right? This would. So I don't, anyway, I prefer to use the verticals. It doesn't matter at the end of the day. Right. Second, we integrate to find the moment of inertia. For example, given the element shown in the figure above, which was the one that we were talking about, right? This guy right here. I know it's not on this slide, but that's the figure we're talking about. Right. So if we're doing the y-axis, remember the equation for the y-axis is the integral of x times dA, right? And so if I was to look here, right, I get y times dx, but y is equal to, what did we say, x squared plus 1? Um, we're just leaving it as y, right? So if we look at this figure, we have a rectangle that is y tall by dx wide, so the area would be y times dx. Wrong way. So there we go. We get integral of x squared plus x squared times y dx. And in the x direction, we just take the integral of, we'll go back to our equation, right? We take the integral of x squared dA, right? In this case, we've taken the integral of the derivative of ix, which is pretty meaningless as far as mathematical speak goes, because yeah, sure, ix should be equal to the integral of its derivative. But what that gets us is the integral of 1 cubed y, 1 over 3 y cubed dx. And that's coming from the parallel axis theorem, which we haven't talked about, but we will talk about in a little bit. So preview. What's the parallel axis theorem? You guys stick around, find out. That's how I keep you hooked today. Since differential element is dx, y needs to be expressed in terms of x, right? We already know this, right? So again, you have to match your differential element, right? You want everything to be in terms of your differential element, because when we take the integral, taking a partial integral, we want to take a full integral, and partial integrals really aren't even useful, right? But there we are. Okay, so let's just do one. Here we go. All right, so I've got this. I want the shaded area shown in this figure, and I want the moment of inertia of the area about the x and y axes. So I want ix and iy. That's what I want. So first thing that I need to do is draw my rectangle, right? But we'll get there in a second. Okay. Everybody's got this. But Dr. D, that says y cubed is equal to x squared. That doesn't look like that to me. I, uh, it's over from 0 to 1. So I mean, if you were to extend that over a larger range, maybe it looks different and it starts doing weird stuff. But as drawn, I'm going to take it for its word that that's what the thing is. Okay. Great. So here we got our thing. We're going to start off by taking our generic thing, and I'm going to use horizontals. Why? To prove that it can be done. But also, why not? I will also go over the other way, but we're going to go after ix first, right? So if that's the case, then this has to be dy, right? Yeah. The height to the center here is going to be our y tilde. And this is going to be x, right? Yeah. And this distance, we'll say, is 1 minus x. Everybody's tracking with me so far, right? We good? Is that really x? I mean, for a given y, that would really be, shouldn't that be like x squared? Because if I'm at y, shouldn't that be x squared? We're just going to leave it as x for now. We'll deal with that in a second. Okay, so far everybody's tracking, right? We're good. Right, so step one is identify dA, right? Yeah, what's up, Ron? Right here? Yes, sorry, let's move that out of the way. Yes, this is it's the y-axis. Good question. You need to know where that is for sure. Otherwise, we don't know where we're measuring from, right? Remember that, call that point. The origin, we'll call it O. Very creative naming. All right, so dA. We're going to say it's 1 minus x dy, right? So why are we using 1 minus x instead of the whole length? Because anytime that I move over, it's 1. That the top of that rectangle is going to be 1 minus x away. Okay. We're just going to keep moving this. This will always be 1 minus x, right? Whatever that happens to be, even down here in these small areas. So we plug in, right? Because this is dy, right? Because for finding the area of this rectangle, that's what we're doing. 1 minus y to the 3 halves. So I just took this and said that x has to be equal to, right? I take the square root of this. That's the 1/2 power. Y to 3 halves. Drew this backwards, and let's revisit this because I did this backwards and it's gonna mess people up. This distance is x. How do I know that that distance is x? Well, if I were to plot this point on this curve, anywhere that this curve touches has to be x because anywhere the other touches is y, right? Right? Does everybody track with that? Okay, so what's left over on the other side is 1 minus x. Okay, that's why we're using 1 minus x. Does that make sense? I'm sorry for drawing that backwards. That would confuse everybody. And then everyone will get to the quiz and be like, okay, or your homework. Yep. Anyway, very good. Now that we've got that cleared up, I will send formal apology letters to your houses. I'll get your SSCs to send them out. 1 minus x from here to here. Okay. So far so good, right? We find our area. We see that our differential is in terms of y, and so we need everything else in terms of y. We take the function, we solve for x, we plug that in to our thing, right? And then we're going to put this into our ix equation. As a reminder, our ix equation is the integral of y squared dA, right? We know what dA is, so we're going to throw dA in here, and we'll get something that looks very beautiful like this, right? And we're going to integrate between 0 and 1 because all of the example problems in the book like to go from 0 to 1. Why? Because those are easy numbers for me to crunch. Okay? Does it always go from 0 to 1? No. It can go from whatever to whatever. It doesn't matter. All right. So we take this and we're going to take, well, I would recommend that you multiply through first and then do the integral. If you were to do both of those things at once instead of me showing you how to do it piecewise. So what did I do? Multiplied by y, y squared, right? So remember when you multiply two variables with with exponents, you add them, right? And so instead of writing that as y squared, I would write that as y to the 4 halves, which would give me 7 halves, right? Is that correct? Did I do that the right way? Yeah. And then 2 over 2 is 1, right? So you have to subtract 2 over 2 from that if I was taking the derivative. So the antiderivative would be adding 2 over 2, which is where the 9 comes from. Does that make sense? It's very convoluted because we're using fractional exponents, right? Well, not convoluted. It's just you got to think about it. You got to think about it. Then we're going to evaluate this from 0 to 1. They wouldn't let me put in a full evaluation line, and that's all I got. But this, I assure you, is meant to show you that we are evaluating this whole expression from 0 to 1, which is really nice that we're using 0 and 1, because then it's just, 1 cubed is 1, and 1 to the 9 halves is also 1. So great. And we end up with 1/3 minus 2/9, right? Whole thing minus 0 because of the 0. I just didn't put the 0 part in there, right? Because it's assumed that that's okay. When I subtract this, I'm left with 1/9 meters to the 4th. IX. 1/9 is like yeah, like 0.111, something like that. Yeah. 0.1 repeating, of course, for Leroy Jenkins. Anyway. Cool, cool. Any questions on this right now as is? Colin. So IX and IY are specifically for translational elements. So think of it as, it's hard to conceptualize it because of the units. One of the reasons that that we will find this is because we're able to talk about things like radius of gyration, which I think make a little bit more sense. But think of it as how much resistance do we have to motion about the x-axis, IX, right? IY is specifically how much resistance to rotational motion do we have about the axis, right? And the polar is always to the origin, right? So how much resistance to the motion do we have about the origin, right? And so the lower the number is for moment of inertia, the easier it should be for us to rotate around that axis. Okay, that's kind of the concept behind this, right? Um, so ideally, right? Well, not ideally. Depending on your system, you might want a high or a low moment of inertia, depending on what you're trying to accomplish, right? Sorry. So now, sorry, sorry. Let's go back. Any other question on this before we switch gears? Okay. How do we do IY? Is that it? So this one specifically asks us to solve for x and y right here. If we have x and y, we can solve for j because j naught or j0 or j origin, j of the polar is ix plus iy, right? So blast through that. Now we're going to do the y direction one, and we're going to use a vertical for this, right? And so if I do my vertical here, right, we are going to say, hey, and this is the reason why I prefer verticals, because I get this. And I don't have to deal with 1 minuses and things. Now, you can say, well, Dr. D, that's not true. There exist geometries where that's true. Fine. Acknowledged. Okay. But anyway, here we are. All right. This is y because this goes right up to where it touches the curve, right? This is dx because it's differential in the x direction, right? And so now that so again, going after iy, well, couldn't we have just used the other thing and done horizontals for iy? Sure, you could have. It's another way you could have done it. We're going to do it this way, right? So dA is y times dx. That means that if we plug in, right, we solve for y here, we get y is equal to x to the 2/3, right? So we get x to the 2/3 dx, right? I just plug it right in. I want everything in terms of dx, right? Okay, and then Iy is equal to the integral of x squared dA, which is equal to x squared times x to the 2/3 dx, right? So that would be 6/6. Yeah, x to the 6/3. So when we put this together, it should be x to the 8/3. We're going to take the integral between 0 and 1 still, because that's where we're at. And so here we go, right? We take the antiderivative of x to the 8/3, right? So remember the process for taking antiderivative it's a mind puzzle. It is, hey, I know that this is the derivative of the thing that I took the integral of. What would that thing have to be, right? So essentially, you have to bring down the 11, the 3/11ths, right, from the previous one, and add one instead of subtract one, right? And adding one is adding 3/3, which is why we get 11/3. Super fun. 3/11ths, m to the fourth. 3/11ths is like 0.233 or something like that. 0.273, sorry. It's way off. 0.27 repeating, actually, if we're going to be exact about it. Okay. And there it is. You have Ix and you have Iy. If we really wanted to, you could add those together and make the polar. But we weren't asked to do that, so we're not going to. And so let's check this out. Guess what? If I wanted to do the above example and find Ix by using a vertical strip, I could. Check this out. Ix would then be 1/3 y cubed dx, right? And we integrate that, we would have to put in our y cubed for, we have to put in y cubed for, wait for it, I'll get there. X squared is equal to y cubed because our function, right? And so the x squared goes in there. Now everything's in terms of x. We integrate, and there we have it. 0.111, which is 1/9. Okay. Where does this come from? This 1/3 y cubed? Okay, great question. I'm going to go back here. Ix is the integral of y squared dA. Yes? Okay. What's dA in this? dA is y times dx, which is where the y cubed comes from. Why is there a 1/3 there? Why is there a 1/3 there? Oh my gosh. Because whoever did this is a real jerk. That's why. So let's deal with this for a second. So this is Ix is equal to integral of y cubed dx. I'm going to leave out the 1/3 for now. Why? Well, we'll see in a second, right? Right, so squared dx. So where does the third come from? Yeah. Any ideas on where the 1/3 comes from? Magic is not a good answer. You would think, right? But All right, because if I integrate this, yes, if I integrate this, I should get, you know what, it is. They put it in there for some reason. They put it in there before they took the integral, because I took this from the book. But anyway, so if I integrate this, I end up with 1/3 times x. No, because it should be 1/3 times 1/3. That's the only way we get 1/9. Why is that 1/3 there? That's going to bug me because I am not magic. Magic. That's not going to fly. No, it's probably going to be on there. Probably this exact problem. And the question is going to be explained to me why it's 1/3. No, you're going to have to explain it. That's the whole 150 points explain why there's 1/3. Okay. Yeah. It has to do with, it's going to have to do with the transformation of using a horizontal versus a vertical. But it's escaping me for right now. So I will get back to you on that. But for right now, the important thing is you don't have to do it that way. You can do it the other way, and it works out. All right, that's a great answer, and probably is going to go in the EOX for sure. Okay, let's talk about something that's useful. Parallel axis theorem. Okay, why do I care about parallel axis theorem? Probably because I have some axis that's parallel to something and I want to do something with it. Great, great. So let me ask you this. When I open the door, do you care about the rotation about the center of the door? Or do you care about the rotation around the hinge of the door? Hinge. So I need a reliable way to be able to convert what is the moment of inertia around the axis of rotation for a specific object. And that is why parallel axis theorem is useful, right? It relates the moment of inertia to an axis passing through the area's centroid to a corresponding parallel axis, right? So in this case, if we use the door example, the centroid of this door would hopefully be dead center of the door because it's a rectangle. It's probably not exactly in the dead center because this door, is this one of the push open doors or does this one actually have a handle? I don't even know. Has a handle, right? So it's probably dead center. The handle's probably going to skew it a little bit towards the handle just because there's more stuff sticking. Might pull it off the door a little bit, but let's assume those are negligible and it's a rectangle, so it's dead center. Okay, great. That's the centroidal axis. The hinge, even though it's up at the top for this one because it uses a damper system and not a full-on hinge, is going to be parallel to that. So we can convert our stuff. So if we have our area here again, our differential area, which is this gray, it's hard to see on this figure. So let's look right here, this gray piece. We're taking this little gray portion right here, and I've defined x prime and y prime. Notice my origin is down here, and the axis that goes through my centroid is denoted as x prime, y prime. So the prime axes are my centroidal axes, okay? Great. I want to say, you know what, knowing the moment of inertia around here is great, but really, we're rotating about here, right? So I need to know what is the moment of inertia. How easy is it for me to move around the origin, not around the centroid of my part, okay? And whenever you look, and I didn't bring my textbook today, but whenever you look at these tables that show you where the moment of inertia is for a given shape, right? It will tell you based off of the shape, not based off of some other coordinate. And so you can find it for that shape, but you might need to shift that using the parallel axis theorem, okay? So the whole idea here is that moment of inertia is tied to this shape, right, when I calculate it. But I don't care about the effect of this rotating about its center. I care about where it's actually going to be rotating, right? Another example would be think about tetherball, right? You care about how that's spinning around tied to the rope, not necessarily how the ball is spinning, although I guess professional tetherball players would argue with me about that, but that's fine. So how do we do this, right? IX, we go back, we do our integral for our area, right? Um, and normally we would use, if we were just using the shape, we would use y squared dA, right? In the x direction. But what do we have? Well, we are offset. We are offset a little bit here. And I say a little bit because we're using d, and really it's a distance, not a differential. So notice we are some distance d away from O. And so we can break this into x and y components. And really, if I'm worried about what the effect is about here, it's not just, I need to map this from O, right? And so the distance isn't y squared. The distance is dy plus y prime squared, right? So the distance from here all the way up is this distance y plus this distance y prime. Does that make sense? Is everybody tracking with me? Yeah? So really we're saying, okay, normally I would be taking this from the center of the centroid part, right? And if I take this from the centroid of my part, the distance, the y distance is just y, right? Whatever that y prime is, okay? And we would say y prime squared. In this case, because we're worried about this point O, we need the y distance from O up to dA, okay? Okay, so we can then take the integral of this, right? Because integrals are linear operators, right? We can take the integral of each part, right? And then, or we can FOIL this and then take the integral of each of the parts that we add together, right? And so that actually makes it a little bit nicer for us to work with, right? Because then we can do 3 integrals of singular polynomial terms, right? There's no weird terms that we have to worry about. Using the definition of a centroid from last class, right? We have this. And now since C is at the origin of the part, then y prime is equal to 0. And we get this. And therefore, this is the big result, the big reveal. Ix is equal to I bar x prime plus a times dy. That's plus dy squared. This is a subscript for y squared. Okay, so weird. Why is this? I don't know why that shouldn't be a subscript there. This should be d squared. A times d squared. Why should that be a times d squared? Units. This is length to the fourth. This has to be length to the fourth. Yes? So it's not a subscript. These have to be squared. So this is a big idea, right? Why? Because you have to do this integration, okay? You can look up, say this is a square. I can look up what is the moment of inertia about the x-axis for my square, right? I figure that out. What is that? That is I bar x prime, right? This shape is my prime shape, okay? It's defined by the prime axes. It is a distance, if I want to incorporate what the effect of the moment of inertia about another point that is a parallel axis to that, it is the area of the original shape times the distance I am away from that axis squared. So it is the original moment of inertia plus the area times the distance away squared. Does that make sense? Well, maybe it doesn't make sense why that's the case, and that's fine. But do you understand what I am saying with this? Okay, so normally we would have some shape here, right? And it can be whatever. Let's say it's just a square, right? Oh, that would have been really bad. That would have been very sad. Let's draw it over here. if I had a square, my centroid would be here, right? And I'm going to call this X and Y prime. The center of my square is there. I can find the moment of inertia for a square. I think it's tabulated somewhere. I'm forgetting what it is off the top of my head, and I apologize. Here's a different coordinate system that is global. And I'm going to call it global because its origin is someplace else. But let's say I have this thing set up, and this, let's say that's connected to its center by some arm, and I'm going to spin this in a circle around the y-axis, right? For reasons. Okay. Well, I don't really care about how it rotates around C, right? I care how this is going to rotate about O. In order for me to figure out what my moment, how easy it is, right? Because that's what Ix and Iy tell me. How easy is it to spin here? We're calling this dx and this dy, okay? Maybe that's a little bit easier to see. I don't know. So this has some moment of inertia that we can calculate. Let's forget what it is off the top of my head, but you can look up moment of inertia for a square. The moment of inertia of our initial object in the x direction is what we're going to call Ix prime. Okay? If I want the total moment of inertia, Ix bar, right? Oh, sorry, we're calling this one bar. If I want the total moment of inertia in the x direction, I have to add the area of this, right? So times the distance in the y direction squared. Why is it the y direction squared? Because it's how far I am off of the x-axis. Right? I want to know how this rotates around the x-axis with Ix. So it's how far away from the x-axis I am, which makes it the y direction. Okay? Same thing for the y direction, I would use that x distance. Now, an interesting thing happens here, and I think that this is easy for, I think you can kind of get an intuitive feeling for the effects here, right? So if I'm talking about spinning something, right, it turns out that the moment of inertia increases the further away I get from my parallel axis, meaning it becomes harder for me to rotate something further away from the axis of rotation, right? And I think that makes sense, right? If you had a long string or a rope with a weight attached to the end, and I told you to start spinning it around in a circle, it would take you a minute to get that going, right? Because the moment of inertia is really large. But if I was to shorten that rope and make it really close to you, it would be a lot easier for you to spin it around, right? If you were a figure skater and your arms were all the way out, it would be harder for you to spin around in a circle. But if your arms and the rest of your body come all the way in, right? Another way of thinking about moment of inertia is and these are area moment of inertia. We can talk about mass moments of inertia, right? And a mass moment of inertia is how is my mass distributed away from the center, right? That's another way that we moment of inertia is to tell us how much mass is out towards the edge and how close is it to the center, right? That's another thing that we can do. If you wanted to use the polar, notice this doesn't change. It's always AD squared. Well, in this case, you're using the polar, so it's the hypotenuse, right? But remember, this is just Ix plus Iy, right? Okay. That's a big idea. And it really helps us out a lot when we're not, because there's a lot of things that that rotate that don't go around the center of rotation is not on the body, right? Okay. What about radius of gyration? Okay. If I have some area and its moment of inertia, and we'll say it's Ix, imagine that the entire area is located at a distance k away. So, all right, I'm going to take, this is, I think, more intuitive when you're talking about mass, but we'll talk about it as a function of area. So let's say I'm going to take, all of this area, right? I've got this big area, and I'm going to say, I am curious if I were to condense that area into just like a singular point, how far away would it have to be from the axis of rotation to net me the same effect, right? So I'm going to take all of my area and I'm going to estimate it as a point. I know it's drawn as a rectangle here, and that's fine. And I'm going to move it away from the axis. What is that distance in which I would have to be spinning it for it to mimic the same effect of the original area? Okay. Like I said, I think this is easier to talk about with mass. And with mass moment of inertia, it makes a lot of sense, right? If I take all my mass and I condense it into a point for any object, how far away do I have to be to get the same rotation as if it were at its original distance? And that's what radius of gyration is. We are estimating a single length to determine that distance away from our axis that I could create I could take all that area or that mass, condense it to a single point. How far away would I have to be? The reason that that's usable and easy to do, well, not easy to do, the reason that we are interested in doing this is because there is an easy relationship that allows us to get Ix and Iy from this. Turns out that Ix is equal to the radius of gyration about the x-axis squared times the area. So you can, if you're given k, you just need to find the area of whatever it is that you are looking for, right? And then you have Ix or Iy, right? The same deal as if you have Ix and the area, you can determine what Kx is, right? So if a problem tells you that you have the radius of gyration about the x-axis, that's what it's telling you. And that makes calculating the moment of inertia a lot simpler, right? And you can do it for the polar as well, or in the y direction as well. Or in the z direction if you ever end up doing really gross three-dimensional moment of inertia problems. Radius of gyration has units of length and gives an indication of the spread of the area from the axes. So closer to the axes means that your area has more area. There's more shape closer to the axis than there is far away. And if it's further away, it means you have more shape further away, right? Again, I think it is more interesting to talk about it in terms of mass, right? So the further away the radius of gyration is when we're talking about the mass moment of inertia, right? The more mass you have further away from the axis, and the closer it is, the more mass you have close to the axis, right? But neither here nor there, right? Really, same idea. Come on, come on. All right. Moment of inertia for composite areas. Okay. So, what do you guys think this is the same or different from finding the centroid for composite areas? It's pretty much the same. All right. So you're going to find the moment of inertia of each of the parts, and then we're gonna do some stuff, right? So composite area is made by adding or subtracting a series of simple shapes. So guess what? You pick the shapes and then you go to the back of the book and you look up what the moment of inertia is for those shapes, right? Or the table or whatever you have. And then you calculate what those are and we do the thing. So how do we do this? Well, first, divide your area into simpler shapes, right? So in this case, you'll notice I like this graphic, right? You would have a rectangle minus a circle, right? Because it's an area. Great. Then you locate the centroid for each of the parts and indicate the perpendicular distance they are away, right, from the centroid of the desired reference axis. Okay. Then you determine the moment of inertia for each of these simpler shaped parts about the desired reference axis using the parallel axis theorem, right? So this is where parallel axis theorem comes into play, because the rectangular part you're not really too worried about, but the circular part that's going to come in, right? The MOI of the entire object about the reference axis is determined by performing an algebraic summation. So you're going to add them. You add all the things, add all the moments of inertia, and then you're good. Right? This is why it's important to understand where your reference axis is. Because the origin is at the bottom left corner of this rectangle, you need to use parallel axis theorem for both of these things. If it were at the dead center, then you would just use the moment of inertia without the parallel axis theorem, right? Because we're interested in what the moment of inertia is around the center of the object. Okay. Remember, cuts are negative areas, right? So subtract cuts or keep them negative and just add everything together, because adding a negative is the same as subtraction. More you know. Sure. Next time. All right, let's just do one. Let's just do one. I have this beam, and the cross-sectional area is given as such. I want to find the moment of inertia of the area about the x-axis and the radius of gyration about the x-axis, k sub x. So I don't need to do any of the y-axis stuff, mainly because if you look at the y-axis, it's going through the center of the entire part, right? So, but anyway, we were asked for x-axis stuff, so we're just going to do the x-axis stuff. So first things first, let's separate this into simpler shapes. Since we're talking about the cross-sectional area, right? This looks like 3 rectangles to me. I'm going to call them 1, 2, and 3. Crazy. Some crazy stuff, man. All right, step 1. What are the centroids of these rectangles? I know it might be hard to see, so let me draw this right here because of the blue arrows that were here. I want you to notice that this is my x-axis and this is my y-axis. So remember, we want the centroid of each of the rectangles as defined from our x and y axes. So if I'm looking at rectangle 1, the one on the top. Oh, that was weird. I didn't like that. I didn't know that this was multi-touch. There. What's the centroid of rectangle 1? What's the x direction distance? Zero meters. I'll probably leave it in millimeters. Either way, it's still 0. I convert that pretty quick. All right. What about the y? So it'd be 150 plus 25. Yep, looks right to me. I'm going to throw you a curveball now. What's the centroid of this one? Yep, this is 3. What about the second one? Should be 0, 0, right? So if you have the option to choose where your coordinate system is, I would recommend zeroing out one of your centroids. That's what I would recommend doing. Now, do we need the x and the y distances here if we're only looking for x direction moments of inertia? The answer is no. We really only need the y distances, right? And why do we only need the y distances? Because Ix is a function of y, right? Remember, it's the perpendicular distance, right? So there we go. The centroids of these 3 rectangles are in their center. The distances from these centers to the x-axis are 175, 0, and negative 175, respectively, which we have done. We did it. Again, we found the x direction one. It's not a big lift, in my opinion, to determine what the x direction centroid is for the rectangle, right? But we didn't need it. But we could have needed it, right? This is very easily could have said find Ix, Iy, Kx, Ky, and J, right? But it doesn't. Anyway, so let's keep going. All right, so we're going to use our parallel axis theorem. Turns out that if you were to go into the back of the book, the parallel axis theorem for a rectangle is 1/12 of the base times the height. That is the formula. That one I remember off the top of my head because guess what? This shape comes up quite a bit. And eventually, when you use it enough times, you just remember it, right? So it's 1/12 of the base times height. So we don't, this is important to note. The second one, the middle rectangle, rectangle 2, already the centroid and our coordinate axes are the same. There is no parallel axis theorem for rectangle 2. It's just finding the actual moment of inertia. Okay? I'll say that again. If we were asked, right, so we say our centroid is here, right? Our centroids are along that line. We were asked to find Ix and Iy. Well, that's not I, that's just y. Right? Everybody's with me so far, right? We've got x and y. It's centered at that centroid. The only reason we use parallel axis theorem is if the centroid and the coordinate axes do not align. In this case, for 1/3 of our rectangles, they align. So for this, for rectangle 2, right here, we only calculate I sub x, which is going to be this in a second. I'll show you in a second, right? But in this case, doing parallel axis theorem about this, right? For Ix1 and Ix3, right? So 1 and 3, these two guys, they're equidistant apart, so they should have the same moment of inertia, right? So we get the 1/12 because the I, when we look up I is 1/12 BH cubed, right? 1/12 B base times height cubed is the moment of inertia in the x direction specifically for a rectangle. And this comes from the table. You look it up. Okay? But because these are some distance away, right? We called it y tilde, right? Not x tilde. Because these are some distance y tilde away, we need to deal with this. So we take the area of this rectangle, right? Area of this rectangle is 200 millimeters by 50 millimeters, right? Because they have the same area, same rectangle, times 175 millimeters squared, which is this y tilde distance that we found. Is that making sense to everybody, how we apply parallel axis theorem? You take the area of the rectangle you are using, you take the distance that you are away from the x-axis of the rectangle that you are using. So for ix1 and ix3, we get this very large moment of inertia. This should indicate to us that it is very easy for us to rotate these around the x-axis. That is what it should indicate to us. Because this is, no, sorry. I thought that was a -8 for a second. This is very difficult for us to rotate around the x-axis. Right? Very difficult for us to rotate around the x-axis. Okay, so everybody's cool with this, right? Application of parallel axis theorem, right? In composite cases, it's very common that you will have to apply parallel axis theorem to multiple sections, but you might not have to apply it to all sections. Just be aware of where your centroids are and where your coordinate axes are. Yeah. Mm-hmm. This one right here? This? So right now we're only doing this calculation. Yeah. So this Ix prime is this. It's 1/12 the base times the height cubed, right? And that's because it's a rectangular shape. And it's going to be the same for all of these, the equation. What we've done is we said, because I know that this and this have the same size and the same distance away from the x-axis, this moment of inertia is the same, right? Moment of inertia will never be negative. Will never be negative. Well, he says, and then watch, it'll be negative. From the inside back cover of the book, the mass moment or the moment of inertia of a rectangle about a centroidal axis is 1/12 base times the height. That's what it is. How did they do that? How do we know that? Well, if you really wanted to, I could have you do it with the integration and it would prove for you that it was. I dumped a bunch of examples in the announcements yesterday. One of them actually proves the moment of inertia for a triangle. So if you guys want to take a look at that, you can. All right? And then we have this. So conclusion is that it's easier for us to spin the middle one around than it is the ends. But we want to know the net effect of our moment of inertia, right? We want the net effect of our moment of inertia. Okay. So also, I would like you to notice so it's interesting, the height, right? The height, when we're dealing with this, is much more significant in terms of the effect on the moment of inertia than the length, right? Than the width, however you want to call it. Right? Yeah, come. We want to know what is our moment of inertia about the x-axis. All right, that's what we want to know. Okay, so we add them. We add all of those. And we get this number. And so it turns out that about the x-axis, we have a moment of inertia of 7.291 times 10 to the 8 millimeters to the fourth. It's very big in terms of millimeters. If you were going to convert that to meters, it would be really small because of the fourth. Right? But here we are. So now that we have this, we can solve for radius of gyration, right? And radius of gyration, k sub x should be equal to the square root of ix, so the total ix over the total area. So we have IX, right? We need to find the total area. Well, there are three rectangles. We just add them, find the area of each of the rectangles and add them together. And 144 millimeters, meaning that in order, if you wanted to condense if you were going to put this in a black hole and condense all of this area into a single point, it would have to be 144 millimeters away from the x-axis to distribute that shape, right? Another way of thinking about it is there is more area of this away from the x-axis than there is close to the x-axis. Okay. That's it. So, steps for moments of inertia for areas. For if you have composite ones, right? Same thing that we do for composite centroids. It's a little bit less involved, right? You find all your moments of inertia, you add them up. Those are the moments of inertia. Add the x direction ones with the x direction ones, add the y direction ones with the y direction ones. Don't mix those up. If you're asked to find radius of gyration, use this equation. I know, it's fast and furious. Any questions right now on this stuff, moment of inertia, before we jump into the preparations, the war prep? The lights will turn red in here, just like in a helicopter. No, everyone, we're tracking, we're good. Bottom line is, if and I'll tell you guys this, unless you are using something that has a completely novel shape, it turns out that once somebody does the integral for the shape one time, it is the same every other time, right? And so that's where these tables come in handy. So most of the time when you do this in practice, if you need a moment of inertia, you will look it up. So knowing how to use the tables is the real lesson here, okay? I'm gonna be honest with you, right? Like the number of times anybody is gonna ask you, like you can do it by integration if you want, but most of the time, unless you have a very novel shape that hasn't been characterized, and maybe aerospace you might, right? Because you have some kind of weird angle of departure for your turbine blade or whatnot, or you're gonna try something new there. But for the most part, you can break a lot of things down into simpler shapes and just have it go, right? Um, so, okay. All right, so what's gonna be on here? Internal forces, which leads us to shear and bending moment diagrams, right? So remember about internal forces, the idea here is that there are some forces that we want to map. We want to map how our forces distribute through our system, right? Through our whatever we're looking at. We're interested in understanding where do we see maximum shear, where do we see maximum bending, and where do we see maximum axial forces in certain cases, right? But for the most part, we were focusing on shear and bending moment, right? And specifically, how do I draw that? How do I solve for what I need to know and then draw how the shear develops in a beam and how my bending moment develops in a beam, right? And if anybody's taking MEE 352 in about a week, then this is going to be really useful because you're going to have to do this again. Cables, right? We talked about cable systems, right? How do we apply static analysis to cables, right? And the answer to that is the same way that we do it for method of sections, really, right? The thing about cables is that we typically pin both sides, right? And so we end up with four unknowns, but only three equations. And so we have to make a cut somewhere. The thing that we're typically asked with, um, big thing that we are typically asked when it comes to cable problems is what is the shape, right? What is the shape? So we're looking for distances from a set point, right? We're also typically asked, well, what is the maximum tension, right? Remember, maximum tension will happen at the highest point, right? Um, you can only have a force directed along the cable in tension. We cannot have it in compression. And so if you're doing math and it tells you that it's in compression, you stop and you look at your numbers because go back and look at your calculator because somewhere along the line your fingers became very fat. Okay, stop having so much salt. Drink more water. Okay. Right, friction. Dry friction and belt friction are where we're going to live. We're going to do a belt friction problem in a second and talk about that because I know we didn't really talk about it very much, right? Yesterday we went back over the types of frictional problems that we have, right? We can talk about slipping versus tipping, right? The thing about friction problems in that sense is you'll have four unknowns. And again, it's a two-dimensional problem. You have three equations in 2D. That's it, right? And so how do we get that fourth equation? We need to make an assumption. It's pretty standard, right? Either we're going to assume that it's slipping or we're going to assume that it's tipping. If we assume that it's slipping, well, then we assume that friction is maximum. But if that tells us that our normal force is not on our object, then we know that we chose wrong and we have to assume that tipping is happening. And if tipping happens, then the assumption is that the normal force is applied at the edge, right? Those are the assumptions, and then we check, right? We would assume that if we are tipping, we're not moving, right? We're not sliding, I should say. We'll definitely be moving because we're tipping. If that would be awesome if I could just tilt something and leave it, but it's not how that works, not how physics works, right? But if I'm tipping, right, what I need to understand is that the friction should be less than the maximum, right? Should be less than the maximum. That's our check. The other style of problem that we have is I am pushing a block up an inclined plane, and here's my frictional coefficient. Tell me how much force I need to hold this in place. Or, hey, motion is impending, meaning that I have maximum friction. Or, hey, check this frictional condition against my pushing force to make sure that I am actually not moving or moving, right? Those are kind of the ways that we would do it. For block on an inclined plane, we assume that the normal force is just in the center, right? Wedges, we talked about wedges. Wedges are just blocks on multiple blocks on inclined plane problems, right? So how do we attack wedges? A free body diagram of each of the parts in our wedge problem, right? They're going to be connected by those normal forces and those friction forces. And then we look to see which one has the least number of unknowns that we can solve. And then we work our way through the problem, solving each one individually until we get the answer that we want, or the answer we were asked to find. We should never look for the answer that we want. That implies that there is, it's not ethical. It's not ethical. All right. We talked about centroid, CG, and center of mass, right? And today we talked about moment of inertia. Moment of inertia, I'm gonna be honest with you, is it's a heady topic. Okay, it's one of those ones that I personally wrestled with for a while because I don't think there's a good way to contextualize it. You can't really. The way that I like to think about it is that. What I normally say is that once things start spinning, it becomes less intuitive to understand what it means, right? And so I try to bring it back to a translational analogy. And if you look at Newton's second law, force is equal to mass times acceleration. Well, sum of the forces is equal to the sum of the mass times the acceleration for particle systems, right? And if we look at the rotational analog to that, we have the sum of the moment is equal to I times alpha, where I is our mass moment of inertia. We talked about area moment of inertias, right? And moment of inertias tell us about how our area is distributed about an axis, right? And a larger number, right? Just in the same way, mass, if I had a large mass, if I asked you to tell me which one's going to be easier for you to move, something that has a mass of 50 kilograms or something that has a mass of 500 kilograms, what would you tell me? 50, right? The lighter one will be easier for you to move. And yes, I used lighter even though it's a mass and that's not the appropriate. You guys know that though it scales the same with gravity, it's fine, right? It's weight. In the same way, moment of inertia affects how easy it is for us to rotate something. A large moment of inertia means that we need to provide a more torque or moment to rotate it, and a small one means that there's less moment needed to rotate it, assuming that we have the same acceleration on both objects, right? Okay. If you keep that in mind, then you can kind of contextualize what moment of inertia is doing. It's acting like a mass, right? It's acting like a mass rotationally. Okay. In practice, right, for areas, it is the distribution of the area away from the axis, right? Okay. Centroid, CG, CM. I think these are a little bit more intuitive for us to understand, right? We've been dealing with centroids. Centroid's just the center of a geometry. How is my geometry centered, right? If I have something that skews to the right, I would expect the center of my geometry to move to the right, like a triangle, right? It's not going to be dead center of the triangle, right? It's going to be towards the tall end, the fat end, whatever you want to call it, right? Centroid, CG, and CM will line up if you have something of uniform density. If you don't have something of uniform density, then they won't necessarily. Still might. Okay. Did I forget anything on this list? Is there anything that you guys don't see on this list that you would like to be on this list? All right. Well then, let's do this. Very simple instructions. Draw the shear and bending moment diagram for this. All right. Well, here we go. Shear and bending moment for this particular beam. This one's not terribly awful, right? Does have an applied moment here. What kind of connection do we have at A? Pin, okay. What kind of connection do we have at B? A roller. Remember that if you see something that looks like this, that's a pin. And if you see something that looks like that, it's a rocker or a roller, right? Look for the rounded bottom. Okay, look for the rounded bottom. First thing we do when we have any shear and bending moment diagram problems is what? Yep, free body diagram to find. Yep, we want these reaction forces. We need them in order to figure out what our shear is going to be. So we've got AY and AX, and we've got BY, and I'm going to leave the rest of these. I'm going to leave this as 15 kilonewton per meter. That's 3 meters away. Right, I've got this here, that's 8 kilonewtons. That's another 2 meters. And then I've got this point here, which is 1 meter away. 2 meters. And I'll change my color for the rotation here. This is going to have a moment at this point that is 20 kilonewton meters. Negative 20 kilonewton meters. Okay. So we're going to find the reactions, right? There's no other X direction forces. We should be very comfortable with seeing that that's zero, right? Make sure that you report that it's zero. If it is zero, you still need to report it. Sum the moment at A, right? If I sum the moment at A, I covered up my notebook because reasons. What do I have? Well, summing the moment at A, I've got negative 20 kilonewton right there. That's going to be minus 8 times 3, right? Plus By times 5 minus 45 times 2 plus 1 plus 2 is 5 plus 1.5, 6.5. Distance from here to the center is 1.5 meters. Is everybody tracking with how and why I picked those and how that happened? Again, you could do this at B if you wanted to and find A directly. It doesn't really matter, right? You just need to do one of them. The reason why I did it before I did some of the forces in the Y is because if I crunch these numbers and solve it, I get 67.3. Is that correct? Yep, kilonewton. Then we'll sum the forces in the Y direction. Sum of the forces in Y direction is AY plus BY minus 8 minus 45. This is interesting because we get a negative here. We had so much force pushing up at BY that AY actually has to counter it. It's not a mistake. It's what it is, right? Because 45 plus 8, right, is 53 minus 67.3 gives you 14.3. Sorry, 14. Yeah, no, we're good. Okay. Cool. We got the reactions and now we can go after it. So if you guys want, you can do it by inspection, right? It's fine. By inspection, though, means that it needs to be 100% right to get the points, right? Because there's no work being shown. And if there's no work, I can't check it. So it becomes a binary grading situation. Also, it has this moment here, right? So I would suggest at the very least to understand how that moment plays into this, making at least one cut here, right? Make at least one. Oh, no. No, 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 no. Okay. All right, so I'm gonna redraw my FBD here with my forces appropriately drawn. That goes away. And I end up with 14.3 kilonewton. I'm not doing that one yet. Okay. So that's what we end up with. So I have my one cut there, and we'll do that. Mainly because I feel so, and you guys can tell me if I'm wrong, but personally, I feel pretty confident that the rest of this is pretty easy for me to understand what is happening, right? I've got shear, so I'm going to push down by 14.3. That'll stay constant until I get to the 8. I'll push down by another 8. That stays constant until I get to 67.3. That'll push up, and then we'll have a linear transition of 15 kilonewtons per meter all the way to the end of the beam, right? And we'll talk about that again in a second. And if you don't feel comfortable with what I just said, you can certainly make cuts as you go to prove it. But what's really going to be confusing here is because I see that this is negative, I, I want to say that my moment's going to drop by 20 kilonewton meters, right? But I'm going to double check it because I'm not sure what that moment's going to do. So let's look at cut number one. Cut number one, V1, moment one, and I've got 14.3 kilonewtons, and this thing is 2 meters wide. But I also have my negative 20 kilonewton meters. Okay. So if I'm looking at this, I sum the forces in y direction is equal to 0 is equal to negative 14.3 minus V1, or V1 is equal to negative 14.3 kilonewtons, which is what we thought. That's a negative, not 74. There. Sum of the moment at 1 is equal to 0 is equal to negative 20 plus m plus 14.3 times 2. So M1 is equal to negative 28. So negative 8. No, I'm looking at the wrong one. Yeah, negative 8.6 kilonewton meters, right? So looking at that, I move M1 over, it's negative 20 plus 14.3 times 2, right? Sorry, I wouldn't move M1 over. I move everything else over, M1 stays there. I get negative 14.3 times 2, which is 28.6 plus 20. So negative 28.6 plus 20 leaves me with negative 8.6. If I were to take the cut right before that 20 kilonewton meters, I would be left with negative 28.6, right? So we can see that the effect there is actually additive, right? So if we look at the equation, let's just look at the equation. M1 is equal to negative 14.3 times 2 plus 20, right? We had a negative moment, but that's going to increase our moment at that point by 20 kilonewton meters. Okay. That's great. We're gonna hang on to that up in the corner. I'll do that. Okay. So, whoa, that was weird. That weird. Why did that happen? I don't know. Okay, so any questions about what we did so far? Why we would do that? I would highly recommend taking at least one cut. If you have multiple moments on there, taking cuts around those applied moments just to prove to yourself you understand what direction it's supposed to be going in, because it can be confusing. And I don't want to tell you that there's a blanket way of doing it. You can always check it, right? And there's no rule saying that you have to do everything one way or the other, right? You can use mixed methods here. Let's start with our shear. That's going to be in kilonewtons. Don't forget to label your units, right? What happens in shear here? Well, if we're doing this by inspection, and we proved it over here, right? When I made my cut, we showed that that was 14.3, right? But this is going to drop. The way I like to imagine point load shears is, hey, there's my beam. I just pushed down by 14.3 kilonewton meters. That's going to stay constant, or not kilonewton meters, 14.3 kilonewtons. That's going to stay constant until I get to here. Right, so I didn't draw my lines, but that's fine. This is negative 14.3. I'm going to draw my lines just to have them. I put them on every time that I have a transition of distance, right? This pops down further, right? This now drops by 8. So this is going to be negative 22.3. which brings me to here. If I add 67.3 to negative 22, it's going to pop me up to 45. Well, that is delightful because 15 kilonewtons every meter for 3 meters drops me, right, by 45. There we go. If I was to calculate the area under the curve here, this is going to be negative 28.6. This one's negative 14.3. I broke this up into 2 rectangles instead of leaving it as one because we know that there is some transition of this applied moment right here, right? And remember what the area tells me. It tells me the difference between those 2 points and what my moment is going to be, right? Negative 22, so this is negative 46, no, 44. I could just look at my, be too easy to just look at my notes. Instead, I can make everybody confused by writing it down wrong. And 1/2 of 45 times 3 is 67.5. Remember, that's the area in there. What is the area? Area under shear curve is delta M from point to point. It is the change in the moment. It is not what the moment actually is. It is how it is changing between those 2 points, right? It's how it's changing between those 2 points. All right. So we're going to do our moment. The moment has units of kilonewton meters. Here's my 0 line. And the first thing that we're going to do is we're going to say we go from 0, between 0 and 2 meters, we drop from 0 by 28.6 because it's a negative. Because that's a point loading, we know that we are expecting a linear change from here to here, right? But I calculated M1 at that cut, right? So we drop to negative 28.6, but then because of that applied moment, we pop up to negative 8.6. Then we're going to lose 14.3 to the next point, right? So that brings us down to 22.9, right? Yeah. So now we're at negative 22.9. Then we're going to lose 44.6. Right? So 22.9 minus negative 22.9 minus negative 44.6 drops us like down here to negative 67.5. Straight line in between those. Maybe if I could, let's do that. No. Third time. And then what happens? Now we have a positive 67.5, so we're going to end up back at 0, right, at the end of our beam. But that's a linear portion, right? That's not constant. That's now an equation of a line. And if I take the integral of an equation of a line, I expect a parabola, right? I expect a quadratic function. And so this will be parabolic up to there. Is that how it actually looks? Probably not. That's probably not a great parabola. It was good enough. It's good enough for me to draw it and for you to get a sense of what is happening. Okay? What happens if I have a triangular distributed load? Great. Well, if you have a triangular distributed load, well, then that's a cubic function because the triangular distributed load, when we integrate it, that makes a parabola on the shear and it makes a third order system on, or a third order equation on the moment. Okay? How accurate do I have to be when I draw all of these things? I told you already. as accurate as you can be by hand, right? Like I am more concerned that you understand what it is supposed to be and less concerned that you can draw it with 100% accuracy. Because in the real world, if you ever have to do shear and bending analysis, right, you're likely going to put it into a computer program like not MATLAB, but MATLAB could do it too. But SolidWorks can do this for you. You can set SolidWorks up to do a shear and bending moment diagram for you. It's overly complicated for what it is, and you could probably do it faster by hand for most cases, but you could do it, right? Like, because you have to set it up as a beam element, and then you have to do all this other stuff, right? But you could do it, is the point. You could do it. Any questions on this? Any questions on this? This one, again, is not the most complicated one. There's ones in the homework that were like chained distributed loads, right? And in those cases, when you have, if a beam has a distributed load all across it and it's different shapes, I would recommend doing it by cuts and trying to determine what the actual equation is for your shear and for your moment in that region, and then do the integration on that. Ref. Mhm. So if you had something like this, and say it's going to change the entire thing, right? So it's going to change the whole thing because this is now parabolic, right? And I would argue that based on the information that you have in the equation sheet, you know that this is an extra parabolic area, which is documented for what it is. It's 1/3 base times height to get that. So you can figure out what that is, and you can still do it. Then this would be a cubic. So assuming that that's what it looked like, right? Assuming, because it has to drop by that much, but does it, right? Because if you have this triangular distributed load, this is 1/2 of 15 by 3, which is not that much anymore, right? Which is also going to affect what our reactions and things are. It looks completely different. So it's hard for me. It changes our reactions. So, but by shape, assuming everything else worked out the same and we had the same levels of force, right? Um, that would be extra parabolic. You could find the area for that, right? I would still recommend don't just never write down something that you don't feel comfortable explaining how you got there. Professional tip. Don't do that either. Don't need test point. All right. Cable problem. So if YB is equal to 1.5 feet, determine the largest weight of the crate and its placement X so that neither cable segment AB, BC, or CD is subjected to a tension that exceeds 200 pounds. Okay, couple things to unpack here. This is a weird one, all right, because it's not really a cable problem in the sense that we've done them before, right? So how are we going to attack it? First thing that we're going to do is a free body diagram. All right, so first thing I want you to notice is that A and D are at the same height, right? And so we could do reactions, right? And you could probably find an X or you find the Y component of either A or D, right? But where we're going to start instead is drawing a free body diagram of this plate that the crate is hanging off of. So let's start there. All right, so why would you do that, Dr. D, instead of starting up here? Well, this is 4 unknowns, and I know I can't get all of them. Also, I wasn't asked to get any of those, so maybe I don't need them. Right? The problem doesn't ask for them. Maybe I don't need them. I'm going to start here and see actually what do I need, right? Because everything I'm asked about is contained in this portion, right? I was asked to find X, and I was asked to find the weight of that crate. So let's start there and see what happens. So if we draw a free body diagram for this plate, here's the plate. I'm going to assume that I'm just going to draw this here. Here's my weight. That weight is some distance X away. Is that the correct place to draw it? I don't know. I am just guessing at this point. Which means that the remaining, well, we'll talk about that in a second. And then what do I have? I have 2 cables hanging here. I'm going to call this FB, and I'll call this one FC, right? Okay. We know from the drawing that this plate itself is 3 feet. And so this distance, the remaining distance, needs to be X minus 3 feet, whatever is left over, right? Whatever is not X. Sorry, 3 minus X. It's the total minus the part that we don't know. Really on a roll with these X minus these dimensioning quantities today. Should probably visit the machine shop. Let's see what happens. Okay, is everybody's cool with that so far, right? We good? Yeah. Okay. So I actually don't like to call it that. I'm going to call this BE and CEF because this is connected at point E down here, and this is connected at point F down there. Okay. And they're not drawn exactly correctly either because they should be at the edges of the plate, but it's fine. Let's just do this. So what do I want to do? It's a great question. Static analysis would dictate that I get 3 equations and 3 unknowns here, right? So I can either sum the forces in the X, sum the forces in the Y, or take a moment. Summing the forces in the X direction is going to get us literally no useful information whatsoever. And so we're not going to do that, number 1. Number 2, if I sum the forces in the Y, that still really doesn't help me in any way, right? But maybe we'll do that in a minute. I don't know. We'll see. Let's start with summing the moments. I'm going to sum the moment at E. Set that equal to 0. If I sum the moment at E, right, what forces do I have? Well, I've got a positive FCF, which is 3 meters away. And then I've got the weight, which is X, right? So minus W times X. So we can rearrange this and we can get an expression for FCF. And that's going to tell us that the weight times X divided by 3 is equal to FCF. Similarly, we'll sum the moment about F, set that equal to 0. If I sum the moment about F, I get a negative FBE times 3, and I get a positive weight times X, right? Yeah? 3 minus X, thank you. There we go. Right? It's positive. And so we can rearrange this, right? So we can find an expression for FBE, right? And then FBE is equal to what? the weight divided by 3 times 3 minus x. Ooh, okay, cool. Well, that doesn't help us yet, does it? Nope, not yet, but it will soon. So now we have two options. We can either draw an FBD, right? So I'll clear this off and I'll bring it back in a second. Don't worry, maybe. So now I can either use point C or point B, right? The whole reason I did that was so that I can now do the stuff with the cables here, right? Um, Remember, because it says it up there, none of these can exceed 200 pounds. None of them. So what should we do? Well, because C has a bigger angle, right? I'm going to assume that the tension in C is larger than the tension at B. Okay, does that make sense? Think about it this way. I had to have pulled C down further, right? Which is true. You can see that because YB is 1.5, right? Which means more of the force is taken up by C than is by B, correct? So I'm going to set the maximum tension in CD equal to 200. So let's see what we can do here now. So let's draw another free body diagram. Here's point C. From point C, I've got the tension from C to D. Yeah, C to D. I've also got on this side the tension from C to B. And I should have FCF pulling down here. Again, same, my typical standard thing. If we were to go back to the original drawing, we would see this angle is 45 degrees. How do I know? Well, like I said, we'll go back to the original drawing. I'll show you. It's 3 feet and 3 feet in the X and Y, so it has to be 45 degrees. Similarly, this is a 3 by 1.5, right, from C to B. So we can figure out what that angle is. So let's put this back. You can do that one of two ways. We can say that this is 1.5 by 3, right? Or you can calculate the angle. Just make sure. Yep, 3 on the base, 1.5 tall. Does that make sense? I know that looks like gibberish. It's 1.5. Right? If I really wanted that angle, right, we would say tan inverse of 1.5 divided by 3, which is like 26.87, something like that, 57. Right in there. Yeah. Simple. Have everything we need to get those angles. Okay. So now what? Well, now we look at this and I know TCD, right? We're making the assumption that this is our maximum. So it has to be 200 pounds, right? We don't know TCB and we don't know FCF. So 2 equations, 2 unknowns, right? Let's do it. And remember, this is now a pin, right? We're isolating this as a pin, so we get 2 equations for this, not 3 equations. Because if you take the moment here, you find out everything is zero. Which is true, but not helpful. Sum of the force in the x direction. Sum of the force in the x direction gives me negative TCB times the cosine of 26.57, right? Yeah. Yeah. Plus 200 cosine 45 degrees. So we can solve for TCB. Right. So if we do that, we would get 200 cosine 45 divided by the cosine of 26.57 degrees, which is very clearly, and without calculator needed, equal to 158.11 pounds. No calculator. All up here. Okay. Okay. We can crunch that, and FCF is equal to 212.13 pounds, which is also equal to W times X divided by 3, which is not super useful at this moment, right? Why is it not super useful at this moment? Because it still has two unknowns in it. How is it going to become super useful? When we find FBE. So what's the quick takeaway here, right? So far. Cables can be treated as either method of sections or method of joints, right? We decided not to use a method of sections here, right? We decided to use a method of joints. We're cutting this at joint C. Why? Because we have two unknowns and we're able to solve for both of those forces. We're now going to move to joint B, and we're going to solve for both of those forces, right? And then we'll come back to the original equations that we got for FCF, E, and uh, and solve them simultaneously. That is the idea. Okay. So we don't even need the reactions at all, right? For this. Oh, we're gonna get rid of these. Keep this. We'll keep those and get rid of that. All right, let's move to point A, or sorry, point B. Notice point B, less than 200 pounds, which checks out with what our criteria is, right? All of these tensions have to be 200 pounds or less. A max tension of that. B, used green before. TCB. This is our 26.57 degrees. And then we have TAB. If we look back at the main document, right, this is actually a 345. So we got that. And then down here is F, B, E. Rinse and repeat. Some of the forces in the X, some of the forces in the Y. We need to do both because we need TAB to find out what the sum of the forces in the Y direction are. So we sum the forces X, set it equal to 0, and we are left with a positive TCB times the cosine of 26.57 degrees minus TAB times 4/5, right? Because it's a 3, 4, 5 triangle. We can substitute in for TCB since we already solved that. And this gives us TAB is equal to 176.78 pounds. Once again, that checks out because if it was over 200 pounds, we would have violated the problem statement. And if it's over 200 pounds and you see that, then you should definitely make a note and probably go back and look at your calculations to make sure everything was entered correctly. Sum of the forces of the Y is equal to 0 is equal to 3/5 TAB. In this case, it's minus TCB sine of 26.57 degrees minus FBE. We know everything in there except for FBE, and we will solve for FBE, which turns out to be 35.36 pounds. Okay. Everybody's tracking and with me so far, yes? What if I had started by doing the reactions at A and E? You would have found out that you need more information and you would have kept working through. Probably would have gotten the one at E, or sorry, at D first, right? Because that has the strongest slope, which means it has to be the maximum. So you can find all of the components at E, and then you can move your way around, right? You're just moving your way all the way around the cable system. Okay. Why did I start with the free body diagram of the plate? Because I wanted to see what the deal was with the weight. Like I was asked to find the weight. I was asked to find that distance. That gives me equations, gives me eyes on what I need to determine those two things, right? So remember what equations you're trying to use, right? I would recommend investigating the area or the variables that you're trying to solve for first. See what the math tells you that you need, and then go after those things, right? We knew we were going to need FCF and FBE, and here we are. Okay. Now, two equations, two unknowns, right? So FCF, and so 212.13 is equal to WX over 3, right? We can say, well, you know, W is equal to 3 times 212.13 divided by X, right? And then if we take equation 2 over here, we would say, well, FBE 35.36 is equal to the weight, which is 3 times 212.13 divided by X times 3 minus X, right? And we can algebra that, which is gross, right? But we can do it and multiply through 9 over 9 times 212.3 over X. If we solve this, we get X is equal to 2.57 feet. Plug that back in to the first equation, and we get that W is equal to 247 pounds. Okay, so if we're going to continue with this, it'd be 9 times 2, 12.13 divided by x minus 3 times 2, 12.13 is equal to 35.36. Right, then it's kind of gross fractional math, but you can do it. A better way would have probably gone with solving for x first, but that's fine. Then reciprocal. Okay. Cool. That's a cable problem. That one's more interesting than the other ones we did. So what's the process? Same process as always for static analysis problems, right? Same process as always. Draw a free body diagram, some forces, some moments, find out equations. If you still have unknowns, go to another point, find more equations until you have no unknowns, right? You have 2 minutes. All right. Before y'all head out, this one, I posted the solution to this in the announcements. It's in one of those PDFs with the friction problems, right? So definitely take a look. Definitely take a look. And then this one is just a moment of inertia problem like we just did. You have 3 areas. I'll run through this so you guys can watch the video and see the solution pop up. Okay. So there you go. Okay. Overall, I think it's been a pretty good semester. If you guys need anything, I'll be around today and tomorrow, so feel free to swing by. If you need anything after this semester, you guys know where my office is. Please feel free to drop by. If you see me in the hallway, please say hi. It's just polite. It's really rude if you like look me in the eyes and then walk away in the opposite direction. All that stuff. All right. There you go. You'll get them in July. Yeah.
You probably mentioned I. You probably did. Oh, it's the same. Whatever that class was. Yeah, yeah.